Welcome back, Marauders. This video 9.2 is about the valence share electron pair repulsion model, or VSEPR theory. So Lewis dot structures tell how atoms are connected to each other, but they don't tell us anything about the shape. And the shape of a molecule can be pretty important. So we use VSEPR theory, valence shell electron pair repulsion theory, in order to determine what three-dimensional shape a simple molecule is going to take. So what it stands for is valence shell electron pair repulsion. And what that means is that the valence electrons, those are the ones involved in bonding, they stay in pairs, and they repel each other. So the molecule is going to take the shape that gets those as far apart from each other as possible. So like I just said, molecules get the electron pairs as far from each other as possible. It's a pretty simple theory. And the trick is just to practice it a little bit, practice drawing the Lewis dot structures, and then learn and memorize all the different shapes that are possible. So there's two steps: drawing the Lewis dot structure, and then determining how many electron domains you have. When you're counting electron domains, single, double, and triple bonds each would just count as one electron domain because those electrons are forced to stay in the same region together. And then non-bonding electron pairs also count as one electron domain. So you're going to look at how many electron domains you have around the central atom, and that will determine the electron domain geometry, or the shape that will put those electrons as far from each other as possible. So there's five different shapes that are possible for your electron domain geometry. And so they are linear, which means that these two get as far from each other as possible. They'd be 180 degrees apart. Trigonal planar, where they're all 120 degrees apart. We start getting into more three-dimensional shapes when we get 4 electron domains. They'll take a tetrahedral arrangement. That's a really common shape, so one you want to be very familiar with. The bond angles in the tetrahedral are 109.5, which you do need to remember. Trigonal bipyramidal, so you have something like the trigonal planar here in the middle, and then one above and one below, so that gets the 5 electron domains as far from each other as possible. And then an octahedral, which is occurring when you have 6 electron domains, and they'd all be 90 degrees apart from each other. So these are the basic shapes that the electron domains can take. So let's take a look at a couple examples. The number of electron domains determines the electron domain geometry. However, there's more than just those 5 shapes, because the number of atoms is going to determine the molecular geometry. So for instance, when you have CH4, you have carbon bonded to 4 hydrogens. So we have 4 electron domains. When we have NH3, we have a Lewis dot structure that looks like this. And so in ammonia, NH3, you have 1, 2, 3, 4 electron domains. So each one of these single bonds count as one domain. The non-bonding pairs of electrons also count as one domain. So this has 4 electron domains. And then with water, H2O, you have an oxygen bonded to 2 hydrogens. So here we also have 1, 2, 3, 4 electron domains. So they each have 4 electron domains. This one all with single bonds, here with 3 single bonds, and 1 non-bonding pair, here with 2 single bonds, and 2 non-bonding pairs of electrons. So since they all have 4 electron domains, they're all going to be basically a tetrahedral shape. They're all going to have 4 electron domains, about 109.5 degrees from each other, in order to get as far from each other as possible. However, these are different shapes because this has 4 bonding domains, meaning that the carbon is bonded to 4 things. This has, the NH3 has 1, 2, 3 atoms bonded, so it has 3 bonding domains, and 1 non-bonding domain, this pair of non-bonding electrons. And then with your water, you have 2 bonding and 2 non-bonding. And so what that means is that you actually have 3 different shapes that are going to be occurring. And so the shapes that you'll have are going to look like this. The CH4 is going to be tetrahedral, so both the electron domain and the molecular geometry are going to be the same because you don't have any non-bonding pairs. So you have the 4 atoms getting as far from each other as possible. They'd each be 109.5 degrees apart. With the ammonia, NH3, you have 3 bonding domains and 1 pair of non-bonding electrons. This pair of electrons is still repelling these other atoms or these other electron domains. So it still takes the basic tetrahedral arrangement, but in one of these corners of the tetrahedron, there's just a pair of electrons, and in 3 of the corners, you have other atoms. So this, since there's just a pair of non-bonding electrons here, takes the shape that's called trigonal pyramidal. And then water, remember we had 2 bonding domains and 2 non-bonding domains. So it's still based on the tetrahedral arrangement. The underlying structure still has the electron domains at 109.5 degrees apart. But since 2 of these are non-bonding domains and 2 are bonding, the shape that you can actually see with the atoms, the molecule would be this bent shape. Okay. So all 3 of these shapes are based on the tetrahedral arrangement. When we look at bond angles, we actually see a little bit of variation in it. So same 3 examples, all 3 molecules have tetrahedral electron domain geometry. So that's the underlying shape. Okay. So CH4, since they're all bonding domains, it has 4 hydrogens attached.